In this lesson, we are going to graph rational functions. Now, this should be somewhat of a review for you, but I'd like to highlight some specific points. There is a page that gives notes on this, but we're going to get right into business. Our first example is going to be this rational function. F of x is the quantity x squared minus 4x plus 3 over x squared minus x minus 6. And we want to graph this. Now, I hope that you know at this point that the first thing you should do is probably factor this to see if we can simplify it. And this factors to be x minus 3 times the quantity x minus 1. And then the denominator factors to be the quantity x minus 3 times the quantity x plus 2. Good. And then you should also know at this point that we're going to cancel some things out. Okay, we're going to cancel out that quantity, and our result is going to be x minus 1 over x plus 2. Now we're going to identify some key features. The first key feature is to identify any zero or possibly zeros of the function. Now, what does that mean? So over here, I'm going to write work, and this is not something that you have to do to show all this work, but in case you're not remembering something, this is going to help you. So zeros is found where the function itself is actually equal to 0. That's where the term 0 comes from. And if we have a fraction will be equal to 0 when the numerator is equal to 0 and the denominator is not simultaneously 0. And this, of course, is going to occur at x equals 1. That's where we're going to have a 0. So when I identify the feature, I'm going to identify the point 1, 0 as the x-intercept, or 0. Now we're going to look at the y-intercept. Now the y-intercept is just that. It's where the graph of the function crosses the y-axis. And that's going to happen when x equals 0. And so we substitute 0 in for our function. We substitute 0 in for x for the function. And we get 0 minus 1 over 0 plus 2. And that is going to simplify to be negative 1/2. And we identify the feature, the point. 0 for x, negative 1/2 for y. Now we're going to look at any vertical asymptotes. Okay, you probably, again, remember this, but a vertical asymptote results from the quantity that got left over after we canceled everything out. And so the quantity x plus 2 will result in a vertical asymptote. Specifically, it's where the denominator, the remaining denominator, is going to equal 0. And so in this case, our denominator is x plus 2. And we set that equal to 0, and so x equals negative 2 is the equation for our vertical asymptote. The feature here is not a point, but rather an equation. X equals negative 2. So this graph will not cross through this vertical asymptote. Now let's dive into this vertical asymptote a little bit further. This may be something you didn't cover. Notice our quantity here in the denominator, x plus 2. That has an inherent power of 1 to it. It's not the quantity x plus 2 squared or the quantity x plus 2 to the power of 3. It's just simply the quantity x plus 2 to the power of 1. Now, since that power, 1, is odd, that is going to tell us something about the vertical asymptote. Now, since that power that I've drawn in purple is odd, the graph of f of x is going to approach the asymptote from opposite directions. Now, let me explain what I mean by opposite direction. So let's suppose here we have the set of axes, and then on our set of axes, I have an asymptote, and now I'm going to draw the function. If it approaches in opposite directions, then let's see, here it goes up as it approaches the asymptote from the left, And opposite would mean as we approach from the right-hand side, it's going to go down. Drawn differently, perhaps the one from the left is going down as we approach the vertical asymptote, and then opposite direction would mean from the right, we're going to approach it going upward, like this. So let's store that information and address it when we're ready to draw the graph. Next, we're going to look at a feature called a hole in the graph. Okay, so the hole is going to result from the quantity that got canceled out. So here, the x plus 3 quantity got canceled out. See here, since the x minus 3 was in the denominator, x can never equal 3. So I'm not allowed to have 3 as a value of x in this function. So that's going to result in a hole in our graph. So it's where the canceled quantity, x minus 3 in this case, equals 0, and then that's going to be x equals 3. For this key feature of the hole, we don't just want the x value, that's where the hole is going to occur. We also want the corresponding y value, so I have to figure if I was allowed to plug in 3, f of 3, what would the value be? So that's going to plug into our simplified version here. It would be, if I were allowed to plug it in, 3 minus 1 over 3 plus 2, and that simplifies to be 2/5. And so our ordered pair is 3, 2/5. Now let's see if this graph has a horizontal asymptote. Horizontal asymptote talks about what happens to the function in the end behavior. So what happens in the far right or what happens in the far left of this function. Now you probably remember some trick from pre-calculus or analysis that talks about the degree of the numerator and the degree of the denominator. So here the numerator has a degree of 2 and the denominator has a degree of 2. And if these two polynomials, which are second degree polynomials, are the same degree, then the horizontal asymptote is going to be a ratio of the coefficients. So coefficients. So there is an understood coefficient here to be 1 and also a leading coefficient of 1 to the highest degree term. And so the horizontal asymptote will be y equals 1 over 1 or simply just equal 1. So in a different function, just to make another one up, suppose we had 3x to the power 5 over 6x to the power 5. Then this would also have a horizontal asymptote. See the degree of the leading term, highest term is the same. And so this would have a horizontal asymptote of 3/6 or simplified to be 1/2. The sheet of notes that comes before these examples gives a little bit more explanation of this, and we will explore it more in the future, talking about why that works. So I like to ask whether or not the asymptote is pure. Now what do I mean by pure? So a vertical asymptote, well, the function can never pass through a vertical asymptote, but a function sometimes can pass through a horizontal asymptote locally. Like in the center it could pass through, but remember horizontal asymptote is about the end behavior. So pure, if it's pure, it means the graph will never pass through the horizontal asymptote. And not pure means it will pass the horizontal asymptote locally. It'll pass through it. So how do we determine if the asymptote is in fact pure or not? Well, we're asking, does the function ever equal 1? Does this f of x function ever equal 1? So we set the function, the simplified version of it, x minus 1 over x plus 2, set it equal to 1 to see if this can happen. So what I'm going to do here is cross multiply, and so I have x plus 2 equals x minus 1. I can see from this that the x's cancel out, leaving me with the statement that 2 equals 1, and that is a false statement. That means this cannot happen. F of x cannot equal 1. And so does that mean pure or not pure? It means pure. The function can never equal 1. It can never pass through the horizontal asymptote. So that's going to aid us when we draw this to know that our graph will not touch the horizontal asymptote. Now we're going to graph this, but please don't think that when we are done graphing it, the problem is done. No, no, no. There's going to be a little bit of extra spice at the end of the problem, so please stay tuned. The first thing I'm going to do is plot the 0 of the function, and the 0 in this case is 1, 0. Next, I'm going to plot the y-intercept, which is 0, negative 1 half. We will have a vertical asymptote at x equals negative 2, so I'm going to draw that here. Okay, I'm also going to label that x equals negative 2. We also have a horizontal asymptote, y equals 1. And I'm going to label this also y equals 1. I'm not overly concerned about graphing the hole, but it does aid our drawing, and the hole is going to occur at 3 comma something small. So we just kind of keep that in mind, that the hole is going to be somewhere in that location. Now, based on this, I would like you to tell me, do you think the graph will go like this? Generally speaking, terrible drawing. Or do you think the graph would do something like this? And then hug this way. Terrible graph either way, but I want to talk about why this one cannot be the correct graph. This one cannot be the correct part of the graph for a couple reasons. One, this graph is talking about crossing the x-axis somewhere over here, but if it did cross the x-axis, we would have found that when we computed the zeros. So it can't cross the x-axis again, so this can't be the correct graph. It also can't be the correct graph because this is showing me pass through the horizontal asymptote, and we already discussed that the horizontal asymptote is pure. It can never be passed through. So this portion of the graph is now correct. I want to decide now, will the graph do this? Can it do this? A couple reasons it can't. This would indicate a 0 that we would have found, and so it can't cross the x-axis. This is also wrong because notice that from the right-hand side, we're going down, and from the left-hand side, we are going down, and that would be the same direction. But we don't want the same direction, remember? We want the opposite direction. There we go. These are approaching opposite directions. From the left, the horizontal asymptote, as we approach from the left, the function goes up, and as we approach from the right, the function goes down. That is opposite directions. To finish off here, I'm just going to label some points. 1, 0, that's a key point. And I'm also going to label 0, negative 1 half. And finally, I'll just use an eraser to show that we have a hole. And there we have it. This is the graph of f of x. And now for the little bit of spice that I promised. Okay, let's first take a look at the vertical asymptote. I would like you to write limit statements that would indicate each of the asymptotes. Here we have one asymptote. X equals negative 2. We have one vertical asymptote, that is. Okay, we want to say that the graph is going to go up as we approach from the left. So we're going to turn that into a limit statement. We're going to say the limit as x approaches negative 2 from the left-hand side of our function, that's going to keep getting bigger and bigger and bigger and bigger, and so we're going to say it approaches infinity. We're also going to say that the limit as x approaches -2 from the right-hand side of our function, well, we can see that that is going to go down, and so we're going to say -infinity. So I'm going to require these limit statements to accompany the vertical asymptotes. For the horizontal asymptote of y equals 1, I need two limit statements here as well. Here, that means the end behavior. There are two ends, the right end and the left end. So as x gets larger and larger and larger, so as x approaches infinity of our function, we're going to get closer and closer and closer and closer to 1. If we approach the left end behavior, x approaches -infinity of f of x, that also approaches 1. We could write that as one statement. We could say the limit as x approaches plus or -infinity of our function equals 1. So for the horizontal asymptotes, you are permitted to write just the one statement. And here, because the limit values are different, one grows without bound, one gets smaller without bound, we have to keep it as two separate limit statements. Okay, example number 2, f of x equals, well, I'll let you read it. We have a quadratic on the top and a fourth degree polynomial on the bottom. And we're going to move through this example a little more quickly. First thing first, we need to factor this guy. To factor, we have in our numerator x plus 2 times the quantity x plus 3. In the denominator, we have x plus 1 quantity squared, x minus 2, and finally x plus 3. Okay, you know what to do next. Cancel out the x plus 3s. And then we're left with x plus 2 over the quantity x plus 1 squared times x minus 2. For the 0, we set f of x equal to 0. That means we set the numerator equal to 0, and that tells us that x equals -2. That is the point, -2, 0. Y-intercept means x is equal to 0, and f of 0, what does that come out to be? 2 over 1 squared times a -2, so that comes out to be -1. So that is the ordered pair, 0, -1. Now for the vertical asymptotes, well, we have two quantities left over. Notice that one is to an even power, and one is raised to an odd power. Our two vertical asymptotes are going to be x equals -1, because that makes this quantity go to 0, and the other is x equals 2, because that makes this quantity go to 0. Okay, but since this is even, what do you suppose even will indicate? We will approach the asymptote in the same direction. And this one here is odd, so we will approach the respective asymptote in the opposite direction. The whole, we're looking at this quantity, and so that will result in a whole at x equals -3, and we do have to figure out that if it did exist at -3, where would it exist? And that's going to be, let's do the math here. That's going to be 1 over 20. Plug it into here if you're not convinced, and you will see that it's 1 over 20. Horizontal asymptote. Well, the numerator has the highest degree of 2, and the denominator has the highest degree of 4. So we might say this is bottom heavy. And in that case, when the bottom is heavier than the top, then the horizontal asymptote is going to be y equals 0. And is this pure? Will our function ever pass through the horizontal line y equals 0? Well, you don't have to do much math, because when we computed our zeros, we did just that. We set our function equal to 0 and found that it's going to pass at -2. So you have to be careful. This asymptote is not pure. We will pass through the horizontal asymptote locally here. Let me write it here. Y equals 0, the horizontal asymptote. I do think it's worth noting here that the 0, originally the 0, this quantity is also to an odd power. See, we set the numerator equal to 0. That is also an odd power. And do you know what that indicates for the graph? We know it touches the x-axis. Well, if it's an odd power, it actually will cut through the axis. But if that power were even, it's going to bounce off the x-axis. What does a bounce look like? So a bounce would come and go ping and touch and then bounce off. In a different way, it could be at the bottom and bounce, ping. But our odd power in the numerator associated with the 0 is an indication of how it crosses the x-axis. Okay, let's graph this bad boy. We know that we have an intercept, a y-intercept at 0, -1. We also have a 0 at -2, 0, and I'll label those in a moment. We have some vertical asymptotes. We have a vertical asymptote at -1. And we also have a vertical asymptote at 2. Now, we're ready to draw this. We know we have to hug this asymptote, and we have to hug this asymptote. And we also have to pass to this point. So we get the idea that this is going to hug. I'm terrible sometimes at drawing this. I'm going to make a mistake on purpose here. What did I just do? It will resemble this shape, but I've made a critical error here. Do you see the error that I made? Oops, I crossed the x-axis twice, and the function does not pass there. It only passes at -2. So I made a big whoopsie here. That's better. Now, my graph is horrible because it's all wiggly and everything, but it does give us the general shape. Notice this little swiggle here. You don't need to know that. As long as it's kind of parabolic, as long as it hugs this asymptote and hugs this asymptote and doesn't inappropriately touch the x-axis going through the y-intercept, then you're in good shape. For the vertical asymptote of x equals 2, will the graph hug and then hug, or will it hug and then hug? Which is it? Well, we saw earlier that it has to approach in opposite directions. And I failed to do something here. I failed to draw the horizontal asymptote, which is lying right on top of the x-axis. But I want to do that so I can show my hug feature, y equals 0. I'm ready to hug. Okay, so opposite direction. See, as we approach from the right, it's up. And I'm going to hug, and I'm going to do my best I can. Don't touch, just hug. Okay, good. Now, for the other asymptote at x equals -1, we saw that that's going to approach in the same direction. So that has to come down also from the left, because from the right it's going down. All right, so now our puzzle says, what do we do here? Am I going to come up and touch bounce and then loop around to hug in the left end behavior, or what am I going to do? Well, we know that the 0 was an odd power, so I have to cut through. But now I've cut through, and I still have to hug the asymptote in the far left behavior, and also that hole was -3 comma small. So my graph now is going to kind of go up, but then it has to come back down so that it can hug, not touch, just close, close, close. Oh, it's hard to draw sometimes with this device. And there it is. There's our function of f of x. Now, I could have mentioned this in the other one, and I failed to mention it, so I'll mention it now. Some people ask about how careful must they draw the graph up in this quadrant, so to speak, and you don't have to be too careful. As long as you hug, you don't actually have to plug in some points to get where this graph is actually lying. It could be lying something more like that above. I'm not interested in that kind of detail. I want to see the general shape, the correct intercepts as I have here. The final thing I'm going to do is just label. So I have 0, comma, -1, and I have -2, comma, 0, and it looks like I have all the key features labeled. Okay, last order of business. I have to talk about limit statements. Let's go with the vertical asymptote first. Vertical asymptote. We have 2 of them here. The one asymptote, x equals -1. Okay, 2 statements for that. The limit as x approaches -1 from the left of our function. So it's approaching from the left, it's going to go down, -infinity. Our limit as x approaches -1 from the right-hand side of our function is also going to approach -infinity. So since these limits are the same behavior, they approach the same unbounded behavior in this case, we can actually convert that to one statement and say the limit as x approaches -1 period of f of x will approach -infinity. We only need one statement there. You can keep 2 if you like. X equals 2 was our other vertical asymptote. Here we are definitely required to have 2 limit statements because they approach in opposite directions. As x approaches 2 from the left of f of x, approach 2 from the left, it's going to go down, -infinity. The limit as x approaches 2 from the right of our function is going to approach +infinity. And I'll have to leave the 2 statements like that. All right, we need one more, or maybe more than one. Let's see. Horizontal asymptote. Okay, in this case, the horizontal asymptote, y equals 0. The limit as x gets large without bound, this is the far right end behavior, the function is going to hug or get closer to 0. And the limit as x approaches -infinity of f of x also hugs 0. And so we are permitted to write that as one statement, limit as x approaches plus or minus infinity, left or right behavior, both equal 0. Last example, example 3. Perhaps you should press pause, run through the problem yourself, and then watch the video to check your answers. Press pause now. Okay, here we go. The 0 occurs at -2, 0. And you might notice that this is to an even power, so it's going to bounce. Y-intercept is going to be 0, -4 thirds. there are two vertical asymptotes. One, x equals -1, odd power, opposite direction. X equals 3, odd power, opposite direction. Hole? There is no hole. Nothing got canceled out. I was kind enough to factor it for you as well. Horizontal asymptote? Well, this one's a little more interesting. If I were to expand out the numerator, the leading term would be x squared plus ... In the denominator, if I were to expand it out, the first term is also x squared. Those are the same power, and they both have a coefficient of 1, and 1 over 1 is equal to 1, making our horizontal asymptote y equals 1. What's interesting about this is whether or not it's pure. So remember, we're asking the question, can y ever equal 1? Can our function y ever equal 1? All right, so I'm going to cross multiply and expand at the same time. X squared minus 2x minus 3. Can that equal x squared plus 4x plus 4? Let's do some algebra. Okay, the x squares cancel out, and then I combine x's on the same side, and in the end, I get 6x is equal to -7, and that tells me that x equals -7/6. Let that digest. What does that mean again? It means the asymptote is not pure. It means we will cross the asymptote at this x value's location. Worth noting, that would be the point. -7/6, 1. It will have a y value of 1 at x equals -7/6. Graphic time. We need -4/3, -2, 0. We have some asymptotes. Let's draw them now. The first vertical asymptote was -1. And the other asymptote was at x equals 3. Let's not forget the horizontal asymptote. Y equals 1, silly. And we know that that is not pure. -7/6, 1. Oh, that's going to be helpful. Now the graph. Hug. Now the graph. Hugs here. Has to go through this point. Oh, we're going to do psych. We can't do that. The graph does not cross the horizontal there. The graph does not have an extra 0. Sorry, can't do it. That's more like it. Okay, so we have opposite, same direction. Let's see. Okay, we approach 3 from opposite directions, so this one has to go up because the other one was down. Hug, hug. Ooh, boy, that was close. I almost touched it, but I didn't. I hugged it. Please don't do this when you graph. Please don't come down and like whoosh, do a little hook, because that makes me think that it's going to keep going up, and it doesn't. Okay, now let's take a look at the other side. This is like a Sudoku puzzle of some sort. We know it's going to be opposite direction, so we have to come here. We know we're going to cross or touch at least the horizontal. Looks like we got to cut through it. And then we hit the 0. What happens here? Well, we remember the even power bounce. Bing! And then we're going to come back up to hug in the left end behavior. Oh, how sweet. There it is. That is our last example's graph. And the limit notation. Let it sink in.